Welcome back after lunch, everybody. We're going to introduce the next topic, which is coordinated responses to contaminants of emerging concern, with Dr. Balslaw.
Good afternoon, everyone, and thank you for the invitation to come to SecADM and present on a sister interagency partnership that is coming down the roads that I think there are some significant points of overlap and mutual interest. So this is an interagency effort that is being coordinated by OSTP on contaminants of emerging concern and the National Emerging Contaminants Research Initiative. So a little bit of history and background of why the CEC group is here. CECs were identified in the 2018 budget as a key issue that needs interagency interest and coordination. And they specifically asked that the EPA and Department of Health and Human Services, NIEHS in specific, to lead an effort to identify research gaps in contaminants of emerging concern. This led to an identification that there's a greater need for interagency coordination around environmental health issues. And so, sorry, I skipped a slide. My slides got it in a slightly different order. Wanted to orient you to what we're defining as contaminants of emerging concern. Some of this is guidance that we received in the legislation, so it may not necessarily be what you think a contaminant of emerging concern is, but they are physical, chemical, biological, radiological, or nuclear materials for which there is no regulatory standard. So it doesn't mean that it's a contaminant that we don't know about. It doesn't mean that it's a contaminant that we don't know toxicity for. It means it's one that we don't regulate. There's an acknowledgement that these may be things that we know are toxic in higher doses, but have some toxicity at lower concentrations than previously known or characterized. And in many cases, and in fact, in most cases, these are compounds, chemicals, contaminants for which we do not have any information on human exposures. I think that's one of the major themes of the CEC effort. And these are contaminants that span across the interests of multiple federal agencies, and therefore are issues that would benefit from greater interagency coordination and also greater coordination and communication with public stakeholders. I heard the earlier comment on environmental justice. There's a significant component of this that is building trusting relationships with the affected communities around contaminants of emerging concern, because in many cases, we know there's a concern, but we don't have any information that we can share with that affected community on what is the potential human health risk, what is the potential human health exposure, if you think of the issues in East Palestine, for example. So in the 2018 budget, we were asked to develop a plan for addressing contaminants of emerging concern, and as a result of that, OSTP stood up a task force on contaminants of emerging concern, which wrote a report which focused on three critical gaps, which is the challenges of identifying the chemical, focusing mostly on chemical hazards. What is the chemical nature of the contaminant? What is the potential for human exposure? And what are the potential human health impacts of that? And that report also lays out, but doesn't specifically address, larger areas of challenge around CECs, which is taking that into risk, actual risk assessment, characterization, mitigation. What do you do about it? And that report does identify potential areas for collaboration between agencies. That led to the establishment of what we affectionately call the JEEP. It is a subcommittee of the OSTP Committee on Environment. It's the Subcommittee for Environment, Innovation, and Public Health. It's established in 2020 for interagency coordination around conducting landscape analyses, gap analyses between agencies, carrying mutual strategic planning, coordinating federal research, and recommending policy outcomes as a result of that. There are currently 4 what we call strategy teams within the JEEP. The one we're primarily focusing on today is the contaminants of emerging concern. There's also a PFAS strategy team, which Natalia chairs. We have a sustainable chemistry work group, which the DTT staff are significantly involved with. And most recently, this year, we have stood up a coordination team on veterans' toxic exposures as a coordinating body for the response to the PACT Act, which requires the Veterans Administration to conduct a detailed chemical exposure analysis for veterans utilizing the serum repository and really focusing on the massive burden of exposure that our veterans experience. So the CEC strategy team mission is to coordinate federal programs and activities in response to CECs. Currently, the co-chairs of the team are Ben Place and OSTP, myself, the director of the extramural division here at NIEHS, and Annette Giuseppe Eli from EPA. She is the National Program Director for Chemical Safety and Sustainability. And then our executive secretary is one of the staff members in DERT, Ms. Jenny Collins. We currently have 18 agencies, some sub-agencies, particularly within DoD and HHS, represented on the team with significant contributions from all of these agencies. Also in 2020, the Omnibus Appropriation, the National Defense Authorization Act in 2020, required the OSTP to develop and release a National Emerging Contaminants Research Initiative, aka the NECRI. And so we went through an effort to bring all of these agencies together. We held public forum as well to talk about what are the activities that we are currently doing, how can we matrix those, where are the gaps in that landscape, where are the opportunities for greater coordination and things that we need to do. And that resulted in the publication of the formal NECRI last year. If you just Google OSTP NECRI, you'll find the report. It lays out in greater detail than the 2018 report did the same fundamental issues, but lays out some of the efforts that are currently ongoing within the government and future needs. And so the 5 key topics are on exposure. That's identifying all the way from source to human exposure characterization, effects both on human health and on the environment, risk characterization, mitigation, and risk communication, which is bringing in that community trust piece. The NECRI lays out 5 specific goals, and we've nicely color-coded these for those and also given them a nice little graphical representation. We'll come back to that a little bit later. So the first goal is to decrease the amount of time that it takes to get from there's a contaminant to getting rid of it, to the risk mitigation aspect. Promoting technological innovation and development of new fundamental capabilities to characterize, track, understand, and mitigate contaminants of emerging concern. The third goal is to develop and deploy new tools and approaches to decision-making around CECs. The fourth is the interdisciplinary interagency coordination in CECs amongst our federal as well as non-federal partners. And the fifth is fostering transparency and public trust when communicating about CECs. We're continuing the report has been released, but we're continuing to move from discussion, these are the gaps, these are the challenges that we face, to what specifically are we going to do about CECs. So we have 3 coordination teams within the strategy team. And the first is really focused on the identification piece. So that's utilizing non-targeted analysis, primarily high-res mass spec, and effects-based monitoring, things like the ToxCast molecular screening, to identify what are the compounds that are present, and to apply some level of biological prioritization on potential downstream risks. And then we have a second strategy team on risk characterization, which is identifying the potential for hazard. This is highly reliant on NAMs. And I just pulled one specific theme out of the implementation plan, which is to expand, validate, and adopt rapid risk assessment methods and link data to critical biological endpoints and exposure scenarios. So this is much like the complementary effort that we have going on. This is not just NAMs for screening's sake. This is trying to apply NAMs that in a way that can be used for regulatory decision making. And then we also, in the risk characterization, have some elements around the potential for human and ecosystem exposure. Then the third one, which I think is actually a fairly unique effort within the CECs, and one that has captured larger attention from OSTP, the language in 2020 that called for the NECRI specifically called for us to release interagency joint solicitations. And as we've been developing this, we've had a lot of conversation around how have we historically approached interagency joint solicitation? And the answer is with a lot of pain, and it's very ad hoc. So every time we do it, we have to reinvent the wheel of what are our various policies, procedures, practices, and how do we move forward on this specific problem. And we said, let's elevate that conversation so that before we get into the specific solicitation, we already have an understanding of how we will best work together as federal agencies to craft solicitations, manage them, and make sure that we are all aware of this. So it's not about the specific science, it's much more of a policy practice subcommittee that is really on, how do we just do that interagency coordination piece? That may be actually elevated within OSTP, taken out of our group and applied on a much larger scale across multiple OSTP efforts. So as I alluded to a minute ago, we're working on a plan to get us from a generic research initiative, the NECRI, to specific actions that we're going to take. And this is also part of the congressional language that required us to develop an implementation plan. So we have a draft implementation plan. It's currently in the very last stages. I think there are 2 agencies that are still working it through red line review. And after that, it will go to NSTC review, and hopefully will be published within probably the next month to month and a half, I think. So that should be available soon. This is a very graphical abstract that I pulled out of the implementation plan that highlights the key themes of the NECRI, walks through the goals of the NECRI, and then specifically calls out specific activities that we're going to do both on a short-term and long-term basis, linking those directly to measures of success. So this is not just a plan to do something, but it is anchored in success metrics so that we know that we've actually accomplished something, and then has an appendix which is not intended for public release, but for each activity that we lay out. We have between a 2 and 4 page kind of description of exactly what that project will look like and be, what agencies are going to be involved, what resources and timeline will be available. So that's the fodder for the joint solicitations that we will be releasing. So as I said, everything is linked. So we have a series of short-term and long-term activities, which include outcomes of having a consensus process for identifying CECs that require action, a process to get from there is a CEC here to the need to make a decision to mitigate, a framework to support the utilization of tools and technologies in that risk mitigation, and then the public trust building piece. And each of these is linked back to the individual goals of the original NECRI. So it is very much a matrixed plan. In closing, just to summarize, the contaminants of emerging concern, very broad definition, somewhat nebulous, but they are an increasing interagency focus. There will be a series of, not just a single, but many joint solicitations that will be released. NAMs in particular are a key focus of the work that we are going to be doing in this, and they are a critical tool for us for the potential hazard characterization. And this is a 15-minute overview of 5 years of work that is going to lead into probably several careers worth of work. So there's much more to come in this. And just in closing, I want to thank that original 2018 task force that was formed. Many of those members have moved on to other projects now. Some of them are still part of the key team overseeing the CECs. We've had outstanding contract support from both STIPI, the Science Technology Policy Institute, and the Avanti Corporation, that we could not have had these 2 reports released, 3 reports soon, without their support. And of course, the many members of the interagency work group, the strategy teams, and the coordination teams. So thank you all. So do we do questions, or you want me to sit back down?
Do we have any clarification questions from SACATA members or ad hoc? Dr. Miles?
Thank you. Very nice presentation, Dr. Balshaw. I was wondering if you could go into any detail around the specific criteria that were used to identify those CECs and how they're being prioritized.
Yeah, so this is not a list-making activity. So we do not have a list of CECs. The focus of this is to develop a platform and a framework that can be utilized in future scenarios to identify potential contaminants of emerging concern and to prioritize them based on the potential for impacts on human health or ecosystem health.
Thank you.
Dr. Marty?
So I think this is really fascinating. I'm glad to see it. I think NAMs will really be helpful in this space as well. My question is along the idea of domain of applicability. So do you feel like you can handle a broad range of CECs? Because, I just think of like modeling efforts, and just in our own area, metals for some of our like in silico models are very problematic. So is the scope really good?
Yeah, I mean, it's a really good question, and it's something we struggle with, because the definition is. I mean, we traditionally have focused on chemical contaminants primarily, and in that case, usually organics. But we do recognize we have a much broader remit, and so I think there will be more attention as this unfolds. We'll start with the relatively easier, and then start to tackle the more challenging. But that is part of why we built in. This is not just existing technology. There is a piece of this which is the development of new approaches that will allow us to not to use the NAMS term, but new tools that will allow us to be able to tackle the things that we know are our greater challenge.
Thank you.
Yep.
I would like to welcome to the podium Dr. Vinas.
Thank you. excited to be here. And I was going to say my presentation is going to be a lot more high level because we're just getting started. So just bear with me. And this is an introduction of a newly formed working group at ICVAM that is going to tackle NAMs for PFAS. And this is co-chaired by EPA. We have Kelly Carson of EPA, I believe just the other side of the lake, and Shruti Kamani at FDA. So, and we put this, I stole this from Kelly, and she stole it from that paper. And I believe actually it's interesting that it probably came out of this building, right? Sue Fenton is probably walking around here somewhere now. But we just wanted to show that PFAS is a very, very large class of chemicals. They can be very different. I mean, we're talking thousands of chemicals. They are very good at water and oil repelling, and they're surfactants, and they're surface protectors, and they're used in firefighting foam. So they have some particular characteristics as chemicals that make them really good at doing all this kind of stuff. On the other side, because of those same properties that they have, they can be very persistent in the environment, and that's where we create all these problems. Like, for example, you probably all heard of firefighting foams going into the environment and just contaminating some areas, and they're also in food packaging. I mean, they're really everywhere. There's like thousands of chemicals, literally. So I just wanted to put this. It gives you, that paper is actually really nice if you want any more information. And now I don't have to really explain because Dr. Balcho gave a really good introduction of the JIP. And this is how it all got started. So this is the strategy team for PFAS that is coming out of the White House, the OSTP, and it's this is the report to Congress. We're a little bit behind the CEC group. So the report to Congress that came out in March that you can see here, and is really easy. You can just Google if you're interested. This was requested by Congress. And what it does is gives an overview of the state of the art of the research that is going on at the federal level. So it identifies all the research that's happening, and the goal was also to look at gaps and what is the best path forward that where can we move next. So it was a huge effort as well. They engaged over 60 federal experts to write this report. It's actually a really nice report with a lot of nice information. There was also a request for information where public could submit what they wanted to be added, and that was taken into account. So what happened here, our chair, which is Melanie Buser, was the chair at the time, and she actually came to an ICVAM call, and she presented the strategic report to Congress. So this is just the first figure, just reiterating that PFAS really are everywhere. They're a really large class of chemicals, and they can be very useful for some things, and they can be very persistent too. So it's quite a challenge to deal with them. And that also makes it a challenge for NAMs, like you can probably figure out that that's what's going to happen. And one of the main challenges that came out of this report is that there are different definitions for PFAS, so that makes it even harder. And this is a table. You go from the broader definition, and that's the one that came out of the NDAA. There's an OECD one, and then there was, we just list ones in here, and you can go from many thousands of chemicals to like a few hundreds. So when you're trying to tackle a class of chemicals, that can be pretty challenging. And they have pretty different structures. So some are long, some are short, and that gives them different properties too. So they're gonna have different hazard, potential hazard. So this report, as I mentioned, it really it wanted to show the state of the art of the research and development in the PFAS world. And these are the sections that were specifically called out. They were requested and they were called out as the main ones. The removal of PFAS from the environment, safe destruction or degradation of PFAS, development and deployment of safer and more environmentally friendly alternatives, also understanding the sources of PFAS, and the toxicity, which is the one that you probably are more interested in here, both humans and animals. These are all addressed. This table also comes from the report, and I just put it here. You don't really have to read it, but you have on this side some of the health endpoints that were identified as hazard, and this is like, what is it, like 10 PFAS? And you can see each one of the thoughts is like, okay, you have, for example, this one here. This one. PFHX says, so it's going to affect body weight, it's going to affect respiratory, cardiovascular, and all sorts of things that have been demonstrated. This is based on the literature, kind of a systematic review as well. So you go to a different one, and you can see they're completely different. So very visually, you can see that there's a huge amount of variability in this class of chemicals, which makes it really challenging to understand. There were some shared challenges in all those areas that were addressed in the report, and these are analytical technology, communication, alternatives, mixtures, reporting, shared data systems, and new approach methodologies was actually identified as one of them, specifically calling for PFAS high-throughput assays. They are compounds that, because of their properties, they can be also really challenging to use in vitro assays. So that's part of the fun. And then the ambient levels. And I don't want you to read that, but this is actually from the report. So it was nice to see there is a lot of interest, and it was very obvious that this was needed in the PFAS research. Priority areas for opportunities that were identified. We have also, I'm not going to read it, but it really called out to PFAS-specific high-throughput assays and making the statement that these models will push innovative health-based assessments while also generating data that may allow progress towards the 3 Rs. So as I said, I don't want to forget to mention that Melanie Buser was at OSTP, and April Cleaver, she's now at DOE, were the co-chairs for this report. So this was presented to ICVAM, and it instantly clicked, right? So this is like a perfect fit for ICVAM, and I see them immediately reach out, and there was this, okay, maybe there's really a need here. Maybe there needs to be a new working group to tackle this issue, because it's a perfect fit to the mission of ICVAM. This is just to show you that there's a few efforts, and all these actually come from EPA, and I think all probably the other side of the lake. And so it's not that nobody's looking at it, but it's just a really complex situation. So you can go on and check those papers if you're interested. But as I said, they keep coming because it's really challenging. Starting with the definition. So what are you looking at when you talk PFAS? So the working group was formed. It's just started, like literally. And there are some initial charges and some scope that is being developed. I think I would say it's pretty much done, but it's still under revision. But these are the charges, is pretty much evaluate the state of the science, need to probably decide on a definition, because we want to move forward with which NAMs can we use where, so we need to know on what, right? So probably start with the definition, and look at what's going on nationally and internationally, applying NAMs. What is being regulated now? Is there any requests by agencies that are already being used? Just really identify everything that's going on. And then the scope is going to be, again, reviewing the definitions and figuring out where we are, identifying tests, in basically just like the report was pointing to, identifying the gaps and opportunities. Where can we apply those NAMs and how? And what are they going to tell us? So ideally, follow up with OECD, maybe. Hopefully harmonizing some of those, but again, it's just going to be a lot of work because they're so different. So it'll be very interesting work. We have 3 potential deliveries at the beginning. We're going to have like a sort of a summary white paper kind of draft that informs where we are, where we want to go, and then that might inform an actual workshop where bring a lot of smart people into the room and help tackle those issues, and hopefully come with some solutions that will inform a peer-reviewed paper or something that can be shared. And I'm hoping follow up by some more, actually make a difference in the use of NAMs for PFAS chemicals. And I think that's where we are. So that's about it. There's been a lot of interest, a lot of PFAS interest everywhere. So there's quite a few agencies that have members in the working group. And we're hoping for more. And we'll just go from there. Thank you.
Do we have any clarifying questions from any SICATM or ad hoc members?
I was like, where's the raised hand? Excellent talk, thank you. Just a quick comment on you had a slide where you showed the different PFAS compounds versus like different adverse events, like this big table. So just to be clear, so you said that these are from literature data, right? So it means that when there's nothing in a particular cell of that table, it means that it has not been reported. Doesn't mean that that compound doesn't trigger or doesn't cause a particular event, right? So that there's no report in the literature, correct?
That's a great question, and I would say it's probably both, because some of them were probably tested and not given, so I'll have to go back and check exactly what they did, or Sue Fenton did part of it, so we can just bring her here. But yeah, some of it is just not known, some of it is actually were negatives because they were tested in different platforms.
Dr. Thompson?
Yeah, I just had a clarifying question. You showed the 4 different definitions, and you mentioned your working group is going to be working toward unifying that. Is there one that is kind of swaying this, or one that people are more geared towards, or is it just a process you're going to have to work through? Where's the status on that right now?
Well, I would say probably something that we want to follow really closely is with the regulatory agencies. Maybe they have a lot of efforts going on and grouping them, and that might be a good path forward, because if they're going to be grouped already and by properties or by uses or whatever, that might be a good place to start. But yeah, right now we're just. Because, how do you start with like 20,000 chemicals or 30,000? So you got to cut down someplace, but you also want to make it relevant, that it's going to be useful for regulations and really to identify where hazards are. So I'm not sure if that answers your question, but we're all confused. Thank you.
I have a very nice presentation, by the way. It's a comment and a question at the same time. So just like you said, NAMs would be very useful for studies of PFAS, also because like how else can you study 20,000 chemicals, right? Or 14,000, I think the latest count. So using NAMs can help with that. But here's the question, why always PFAS are studied in a group of PFAS? So you have NAMs, right? And you can study even more than 20,000 at a time. So like even in your table, you're classifying PFAS and you're studying what's the effect of those specific PFAS on health. And you have definitions for PFAS. But the question is, what if what's causing that is not what's making them PFAS in the first place? So that's why I'm asking, like, why PFAS are studied as PFAS as a group based on those definitions separately. Why don't you study them in comparison with other chemicals, bigger families or bigger classes of chemicals, and study similarities with PFAS and other non-PFAS chemicals that share similar structures or similar functional groups and many different similarities to figure out what's causing those effects. Maybe it's not what's making them PFAS in the first place, or maybe it is, but at least it will help identify what's causing those effects.
So if I'm following, I would say that a lot of those effects are actually because of their chemical structure. So, but because they can be long, they can be very different. So I'm not sure how to compare to other classes of, for example, the people that work on QSARs, they don't really work for PFAS because they're just different. So I don't know. I think you need to join the working group.
That's what happens when I open my mouth.
That's what happens.
Thank you, Dr. Vinyas. So we're going to, we now have the section for public comments. There was no written comments received for this session, and there were no oral comments received for this session. So we can proceed to the SECATM discussion. So again, as a reminder, the lead discussants go first, and then we'll open it up to any other SECATM members or ad hoc that want to participate. The lead discussants assigned here are Dr. Baines and Dr. Silvera.
Thank you. So, So first of all, I want to thank the presenters, Dr. Balshar and Dr. Venice, for a great presentation. Very informative. I have to say I'm very excited that there seems to be a big push to move forward with studying these CECs, contaminants of emerging concern, and also PFAS. In terms of the CECs, a third report is coming out in the next month or so. I think that says a lot to the urgency and to commitment of these different agencies to move forward with really trying to get a handle on these CECs. And then PFAS, a working group just got formed, and and I think we all have heard over and over in the news the concerns about PFAS and what we don't know, and the concerns of what what does that look like in the future in terms of health effects. And so I'm very pleased that there seems to be a really big push and effort, swift push and effort to move forward with both of those significant topics, CECs and PFAS. So just wanted to just throw that out there in terms of just saying that I think that's very important. And I like the idea of it being an interagency. So it seems like there's experts from different agencies being involved, which I think is huge. So I just want to first just, again commend you both and just encourage you to continue moving forward with trying to add more knowledge to those topics. So again, congratulations on that. So there was various questions that I wanted to address. One is, how much confidence do we need on a NEMS before deploying it for use in an environmental event or emergency event? So when I think about that question, I was trying to think of potential situations that have happened recently or within a few years. And the first one that pops to my mind is one that happened in February. We had a train derailment, if y'all remember, in East Palestine, Ohio, where train derailed, and I think some tanks turned over and vinyl chloride was released. So that was the first environmental impact accident that I thought about that happened recently. And then I also went back years in my memory and thought about Flint, Michigan. What happened in Flint, Michigan with the high lead that was found in the water supply of that town, which led to unfortunate results. And so, when I think about those types of events, I think about, well, if we are successful with developing NEMS that could potentially, detect toxins in the environment, when those types of incidents happen, either abruptly like the train derailment, or in terms of maintaining, kind of like a surveillance of toxins that are found in the environment. We could develop NEMS that could detect that. How useful that would be as a tool. And so I think when it comes to the confidence of NEMS, I think, just as, we're all scientists, and so, as when it comes to believing the data, believing if an assay works, we need it for it to be validated multiple times. We need, validation. It needs to be reproducible, so validation, reproducible, and you need to get consistent results. Repeating it over and over and again, you should hopefully get the same results. And I think those categories or those factors that are used for any experiment or any assay, needs to be also used to judge, NEMS as well. And so, I think, I think the more we do those things and validate and get consistency and reproducibility and that increases the confidence that you have in NEMS. Again, I think, the more we can prove that, then, and fortunately, we've done that already. We've done it with some NEMS already. And so I think if we continue doing that, that just adds to the body of knowledge of NEMS that we can see moving out and being used for various purposes. So again, I think when it comes to how much confidence do we need? Well, the confidence that we use for any other test or assay, that will dictate the confidence. Now, but I think it's important to also say that just like there's no perfect model, I don't think there's a perfect assay. And so I think sometimes NEMS get the bad end of the stick of it got to be perfect, and I don't know if anything's perfect. So I think we quick to try to put things in black and white, and I think we got to keep in mind that there's different degrees of perfection. And so I think as we move forward with developing more NEMS and validating them, I think again the idea is trying to develop NEMS that will definitely have be validated, confidence be built, and that will lead to it being commonly used more, I think, in the future. So I just wanted to suggest that. Also, in terms of contaminants, again, if we use NEMS for, for an emergency or environmental event, I think we're talking here about, what's getting into like what in the water supply, but we also might need to think about potentially NEMS that could be also used for gases and aerosols as well. So I think we want to keep that in mind as well, in addition to contaminants in the water in terms of in liquids. Let's see. Do we need those to be? And then also, I think it's important to keep in mind that when it comes to detecting environmental events and emergency events, definitely NEMS can be used, and I think would be great for them to be used. I think for a lot of wastewater treatment plants, I think they use fish. They use fish to determine if there's any toxins in the water, and the health of the fish dictates to them what they need to move forward with in terms of if they're need to shut down the water supply because of the health of the fish. And so if we can use NEMS to help with that, then I think that would be great. So again, I think I think it's important to keep in mind that NEMS don't have to be the end all be all to everything that we want to try to do, but it can be also included, or in some cases replace, other methods that we're doing. So I think it's important to keep that in mind as we move forward with keeping in mind the confidence of NEMS. So let's say that. And then, are there other resources currently not considered that can be used in response to contaminant of emerging concerns? So I think, that there's always room for improvement. There's always things that we can think about. I was thinking about COVID, our favorite infectious disease, and how wastewater was used to detect, levels of COVID rise in different communities, and how that seemed to really be a novel idea and was used, during the height of that pandemic. And I was just thinking that we could try to do something similar, as well. Potentially, that might be something that we need to think about, as well with these CECs. Is there something we can use to detect, these CECs that may show up in the environment that we may not be aware of? So just one thing to think about. And then also, I know it talks about resources, but I also want to, again, as a professor, I'm always thinking about students and thinking about how we can incorporate students into this NEM space. I've had conversations with some of my Cicada members yesterday about how, I think it's really important to make sure we get students and trainees, graduate students, undergrad students, graduate students, postdocs, early in learning about NEMS and being exposed to NEMS, because for many of us who are a little bit more mature than others, we were trained a certain way, and a lot of us are set in our ways, and just being honest. And so I think, if we can make sure to bring on board students and trainees, and make sure that NEMS are being, that they're being exposed to NEMS in their classes, in their research, I think that would just help, to really push this space forward even quicker and faster. So that's something else I wanted to say. And then I think we saw, again, from my great presentations, so the question is, are there NEMS that have been shown to be useful in testing PFAS? So I think we just saw from a great presentation from Dr. Venice that, there definitely are NEMS being involved as it relates to high throughput screening. As was said, PFAS, 1,000 compounds, probably way more than that. And the idea is, if you don't use high throughput screening, you're not going to, kind of going back to your question, if you don't use high throughput screening, there's no way you're going to be able to, screen all those different chemicals of PFAS, PFO, and their related cousins. And so high throughput screening, using NEMS for high throughput screening was mentioned, in the CECs, using NEMS for determining potential hazards, risk and hazards. I think, again, I think there's a lot of room for using using NEMS for these various CECs and PFAS. And so again, I'm very pleased with what's been done up to this point. And I believe there's a huge, there's a lot of room for growth, and I hope we keep moving forward in these spaces because, both with PFAS as well as CECs, these are some serious environmental concerns. And as a cancer biologist, again, the idea is, what we're exposed to now can potentially cause issues in our health later as it relates to cancer. So I think the more we can understand and tackle these diseases and contaminants, and learn more about them, the better we all will be as it relates to our health in the future. But again, great job to the efforts that are being done, and look forward to seeing what comes out in the future.
Dr. Silvera?
Yeah, thank you so much to the presenters, and I share most of the comments that my co-discussant just displayed, particularly on the urgency of addressing PFAS and other contaminants on a timely manner how NAMs can help us with this and also complement existing methods. And also, I echo the comment about training and educating the next generation of toxicologists in incorporating these type of tools that certainly will have a positive impact and will help us address these issues faster. I am wondering if when we think about these NAMs and how they can be proven useful to detect these toxicities, we can emphasize the need for consideration of toxicity at multiple levels, particularly those toxicants that have effects on the endocrine system, and maybe digging deeper in how NAMs such as organs on a chip or any other type of methodology that can integrate systems can help us initially complement and potentially replace animal testing and using physiological models. And finally, I have a comment about integrating the two presentations. I think Dr. Viñas provided a very good timeline on how we're going to use NAMs for PFAS risk assessment, and integrating that with the CEC initiative that Dr. Bolshaw presented. I wonder if there could be any plans to incorporate community engagement in this timeline, and particularly communication to affected communities in a timely manner in order to comply with the goal 5 from ECRI, and to prevent issues such as the one that my co-discussant mentioned about the train derailing and the community not being aware on a timely manner, which severely impacts the trust in science from communities. So I think when we think about using these methods and incorporating new ways, we have to always keep the communities in mind and how, as scientists, we have a responsibility to the people that we serve. I think that's all I have, and most of what I was going to say was already covered by my co-discussant, so thank you very much, and great presentation.
Thank you. And we're going to open it up to any other SACATM members or ad hoc members that would like to participate, as well as any speakers that want the opportunity to respond.
So I'd like to respond to the last point that Dr. Silvera raised, and something that Dr. Baines raised as well. And it's the kind of timeline of community engagement and also the certainty of the measures. I think one of the traps that we as scientists fall into is feeling a need for utmost confidence before we're comfortable communicating with the affected communities. We use that as a shield, as reason not to communicate with the communities. And we need to have more respect for the sophistication of the affected communities and their ability to understand uncertainty. Don't hide it. Own the uncertainty in the methods that you're using. These are screens. They're not gold standard approaches. But this is what we're seeing, what we're concerned about, or where we're not concerned based on what we're seeing from this screen. It's unproven. It's uncertain. Communities will accept that if you do it in a trusting manner. That's how you build the trust with the community. So I totally agree with this. It's not a reason to delay engaging with the affected communities.
Thank you. And please remember to use the raise hand feature in the Zoom link too. Dr. Fudge?
Thanks for the excellent talks. Just three comments about the discussion around PFAS. First of all, I would say that when we talk about 5,000, 20,000 PFAS compounds, it is clear that there's no way we're going to be able to test them experimentally, like all of them, to profile them, to characterize them. There's just no way. You would need to hire chemists and have them work for the next few years to just like synthesize all of them. That's just no way it's going to take too much time, too much money. So having at least, and I think that there's a few papers that showing them that the top 10 most abundant PFAS, PFOA, etc., that are in the environment is the first thing to do. There are a few papers out there that list them. The second point is about perhaps we should not try to think about reinventing the wheel here. Like I would love to see a paper, perhaps it exists, but I did not see it, where you get this 10 most abundant PFAS derivatives where you have things like aqueous solubility, soil degradation assay, cellular uptake, metabolism, all in like very nice spreadsheet done in one or two lab with a minimum experimental variability. That would be awesome to just start with that. And there's a lot of QSAR models that can be used for this top 10. And as I really appreciate what Kamel said a few minutes ago about this type of, it's good to look at the PFAS family, but also put that in perspective of other compounds. And it goes back to what we were saying yesterday about those reference chemicals. I think it makes a lot of sense to always compare the PFAS soil degradation versus a known set of compounds with clear soil data, and obviously an industry partner here would be useful, as there's a lot of soil degradation data that are not easily public, but that's why having an industry partner would be great. Thank you.
That's Tom.
Just a few quick points. So just like we heard that it's difficult to test thousands and thousands of PFAS, I think we also struggle with dealing with mixtures of chemicals. And for these contaminants of emerging concern, this is really an area where mixtures should be prioritized. There's data out there on co-occurring PFAS or many, many other contaminants of concern that could be applied in NAMs in proportional mixtures to those that are found in humans, wildlife, and the environment. And method development was mentioned by one of the speakers, and I think this really needs a lot of work, because there's, in the case of PFAS, much of PFAS is called by chemists so-called dark matter, because we lack methods to even find it. So we're looking at the usual suspects over and over again and really do not have an understanding of the full complement of PFAS that are showing up in environmental media and in humans and animals in the wild. Yeah, and just one quick example of that is this top assay, the total oxidizable PFAS, where you blast apart what you have in your sample and you look for differences just based on targeted analysis for methods that you do have. And there's anywhere from like 20 to 30% difference in the total amount of PFAS detected, indicating tons of unknown precursor compounds.
Okay, so it does not look like we have, Dr. Viñas.
I just wanted to add here, and that was a great comment, and I'm trying to remember the number, and I can't, and I'm no chemist, but I remember a conversation with Ben Place from NIST where he was talking about how many you can actually measure, how many PFAS. And I believe he was mentioning that you cannot measure more than like 200 or something, because there's just no standards. So that is a huge challenge. So if you don't know what's there, you really cannot measure it. So it's a really hard problem, especially if you look at mixtures and all that. Yeah.
Okay. So we're going to move on to the next session. The next topic is computational resources. And I would like to welcome Ms. Hull to come up to the podium, please. Oh, sorry, if that wasn't obvious, we are not going to take the break. We're just going to go straight ahead.
All right. Cool. Hi, everybody. My name is Victoria Hall, and I'm a bioinformatician at Innovative, where I work as a contractor supporting NICEDM. And I thank the CICADM Organizing Committee for allowing me to speak about the work we've been doing on the integrated chemical environment. So the Integrated Chemical Environment, or ICE, is an open access GUI-based resource for highly curated toxicologically relevant data and computational tools. And so ICE was developed by NICEDM not only to help with the evaluation, application, and development of new approach methodologies, but also to help democratize data as we aim to take, whoops. I don't know how that happened. Am I not going the right way? How do I go back? Oh, I don't see a keyboard. It's in a drawer. In a drawer? Okay. Oh, there you go. All right, hopefully it doesn't keep doing that. All right, so anyways, we use ICE not only to support the development, application, and evaluation of new approach methodologies, but also to help democratize data as we aim to take these very complex data sets and these complex models and make them accessible to even folks who don't necessarily have the coding or the computational experience necessary to access them otherwise, as they might be intimidating or difficult to navigate. ICE is also developed to support FAIR principles and provide data and tools that are findable, accessible, interoperable, and reusable. And we have 2 releases that have happened in 2023 since the last CICADM release, or the last CICADM meeting, and that is ICE version 4.0 and ICE version 4.0.1, and I'll be focusing on those for the duration of this meeting. If you want to access ICE, either to follow along or just for future reference, we have the QR code shown in the upper right-hand corner here, or the hyperlink shown in the bottom left. So one way to access the ICE data and tools that I'll be talking about is through the ICE webpage itself. And on the home page shown here, you can see that there are icons at the bottom of the screen that will bring you directly to the various tools that you can navigate, as well as the data sets that I'll be discussing. If you ever have more specific questions on how to use those tools or how to navigate the data sets or how the data sets are curated, you can go to the top of the webpage and you can see Help, where we have various in-depth user guides, or Data, where you can read about our curation processes. And I'll be talking about our more recent releases, but if you want specifics on those releases, you can navigate to our ICE release notes, where it will give you very specific detailed breakdowns of what we've added over time. If you ever want to access ICE data outside of the website itself, or if you have very large queries, we recommend using the REST API. And the REST API was added last year, but it has a link provided there. And using that REST API, if you give 1 or more chemical IDs, you can return a list of different assay and endpoint objects. So ICE data consists of in vivo, in vitro, and in silico data that are organized by toxicity endpoints to help aid in your regulatory and exploratory purposes. And here is a table of the in vivo and in vitro data that we have within ICE. And this is curated based on things like ICMA validation, literature searches, database searches, etc. And it is highly curated to help with NAMs. And so many of these data sets have been previously in ICE. They were not necessarily changed in dramatic ways, but we have done a lot of back-end work on our end to continue to harmonize and update these data sets to make sure they're as high confidence as possible. So things this past year, such as making sure that data fields are consistent and data structure is consistent to improve interoperability, or adding in some of our acute inhalation toxicity data that NICEDM has been working to curate, have all gone into past releases to make sure that as you navigate the new approach methodology field, you have access to data that is very high quality. We also have predicted endpoints such as data from in silico models and various integrated approaches, and these are particularly advantageous for filling in data gaps and for accessing chemicals that might necessarily have the experimental data that you need. And so many of these come from OPERA, which Camille will be talking about next, but we also have data from CATMOS, which was something that came up frequently yesterday. I do want to point out in particular that one of our big releases is a new data type of exposure predictions, and this is the first time we have this kind of data in ICE. So with release version 4.0 in March, we added in exposure predictions from EPA SEAM3 model, or the Systematic Empirical Evaluation of Models. And this is for over 475,000 chemicals. And for those chemicals, you can get a population level exposure of predictions, or exposure level predictions in milligrams per kilograms per day at high levels of potential exposure and low levels of potential exposure. And I'll talk about how you can access those in a second. So as you navigate ICE, you might have a chemical in mind that you're looking at in particular, or you might not. And if you don't, then ICE has specifically curated chemical quick lists, both reference lists and non-reference lists, that can help you navigate and explore various data points of interest and endpoints of interest. And so I want to point out here that the new chemical quick list that we have added within 2023 since the last ICADA meeting are a quick list for mixtures and formulations in ICE. We've heard a great deal today and in previous talks about the importance of mixtures. So now you can easily access those mixtures and see what mixtures data we have and what endpoints we have available for those, as well as ToxCast phase 1, phase 2, and E1K data, allowing you to not only explore Tox21 data, but ToxCast data as well as you look through some of these curated high throughput screening assays. Okay, so now I'll briefly walk you through the different steps of our suggested ICE tools in our workflow. I want to say that this is only suggested. This is not the only way you can access ICE. This is not the only way you can access these tools. They can be either used as standalone tools. You can jump in between them, whichever way you want. This is just our suggestion here. And so we recommend starting with our search tool, where you perform a search and see the available data that we have within ICE. Then you can move on to Chemical Quest, where through identifying similar chemicals, you can expand the inventory of chemicals that you're looking at. Then you can move on to our Chemical Characterization tool, where you can look at physicochemical properties and chemical use categories. Then you can go to Curve Surfer, where you can review in vitro data details, including things like bioactivity and mechanistic target. Next, you can go to our PBPK, or physiologically based pharmacokinetic models, where you can generate chemical concentration predictions. And last, we recommend going to IVIVE tool, the in vitro to in vivo extrapolation tool, where you can predict equivalent administered dose from in vitro data. So to perform a search and to kind of start off with this workflow, you can navigate to the input page of the search tool. And so from the input page of the search tool, you can either input your own chemical quick list. You can see up there where you can access the quick list I showed previously, including our new quick list of mixtures and formulations, or ToxCast data. Or you can enter your own chemical identifier. So if you have a chemical of interest specifically, you can input that. And one thing I want to point out is based off of last year's ICADA feedback, beyond being able to just input things like DTXS ID, CAS-RN, and chemical structure, you can now input chemical name and chemical synonyms into that chemical input list. So that is a brand new feature that is intended to make this a little bit more usable. Another thing that you can do is after you input your chemical list, you either do a chemical quick list, or you do a chemical identifier of your own, or you mix and match and do both. You can then click on the Select Datasets button to select assays that are organized by toxicity endpoint. And in doing so, you can access those new and improved datasets that I talked about previously. So after you run that chemical search and after you get to the results page, this is an example of what this may look like. And on the results page, you can see there's a long view and a wide view of the different data points, allowing you to explore our new data sets. You can click the icons to view specific substance details. You can click on the CAS-RN to link out to NIHS subs if you would so like, or you can click on the DTXS IDs to link out to EPA's ComTox dashboard. You can also click icons to help filter results specifically. So if you're dealing with too much data, you think it's a little bit overwhelming, you can help narrow that down a little bit, get a better, more specific output. Another huge thing I want to point out here is that you are able to send these filtered results to other ICE tools, and so making this an interoperable website. And this is not only just in search, but with all of our tools, you're able to take these filtered results and send it to the next step, which allows you to not only follow the workflow, but to make sure that you're keeping consistent between your tools. Okay, so next in our workflow is Chemical Quest, and with Chemical Quest, we haven't made too many updates to this year, so I'm just going to go through it quickly. But if you go through search and you're not necessarily finding the chemical that you're interested in, or we don't have the data point that you're interested in, one way you can kind of address this is through identifying similar chemicals, or chemicals that might have similar structure, to expand that inventory. And with Chemical Quest, you are able to give a chemical input, such as the DTXS IDs or CAS-RNs or chemical names I mentioned before, or you can draw a 2D structure and input a chemical smiles. And after you input that, the results of that are going to show you the number of similar structures identified for each input chemical. And then from there, from looking at those structures, you can then filter it down a little bit further based on things like specific substructures. And when you specify certain smart strings, you can highlight those for easy identification. So you've performed a search, you found some of the data points that are of interest to you, you've expanded out your data set a little bit more using Chemical Quest. Now you can characterize those chemicals based off of our chemical characterization tool. And within the chemical characterization tool, a unique feature of this tool is you can input 1 or 2 chemical lists to compare and contrast. And so you can access physical chemical properties predicted from OPERA. And those are the tables that are shown on the left, where users can input 1 or 2 lists, and then they can toggle results to show 1 or both of the lists. And you can see either those physical chemical properties on a specific chemical level, or you can view a statistical summary of those OPERA predictions for your entire chemical list. You can also view product use categories, which are the products that a chemical has been reported to be found in. This is derived from EPA's Chemicals and Products database. And you can examine that through either a visualization with these bubble graphs that show the hierarchical nature of those product use categories, or you can examine them through these summary details. And one update this year is that these were formerly called consumer use categories. So consumer use categories are rebranded and slightly updated to be called curated product use categories. And this is for a few reasons, one of which is that the product use category name aligns better with the source material of the CP.dot database. But also it helps differentiate from a new type of use that we have input into ICE this year. And so this new type of use is known as functional use. Functional use is the role that a chemical plays within a product. So if product use is the product that a chemical is found in, functional use is the role that that chemical plays. And so this is also derived from EPA's CP.dot, and we have 2 types of functional use in here right now, and that is reported functional use harmonized to OECD use, and predicted use as predicted by Catherine Phillips at EPA's quantitative structure use relationship models, which are random forest models, one versus all models that predict the functional use a chemical may have. And you can either download that data on our datasets page, or you can interact with this data using these new heat map visualizations. And on these heat map visualizations, you can see the number of substances that have a given type of data. If a cell is colored in, that means it has that function, and the color of the cell is going to correspond with which chemical list you input. Okay, so on to the next tool in our workflow is CurveSurfer. CurveSurfer is another tool that has not had a great deal of updates this year, so I'm not going to deal with this too much, but after you've characterized, you've seen the various properties of your chemical, you've seen what uses it may have, you can then go on to CurveSurfer. And CurveSurfer allows you to explore concentration response doses from curated high-throughput screening data derived from EPA's ToxCast and Tox21 libraries. And so for these, you can see these plots that have the key features highlighted, and they give details for assay and chemical information below those plots, including things like AC50 or any potential flags we may have given it. And one of the heavy hitters of this tool is that we have this filter chain. And the filter chain allows users to filter their chemical list based on various properties of that chemical. And it might be something like call, is it inactive or active in specific assays? What is the mechanistic target? What assays is it tested in? What are those assays what question are those assays trying to answer? You can look at things like AC50 to get an idea of how sensitive your chemical may be. And so based off of those filter chains, you can kind of take your chemical list, you can narrow it down based on bioactivity or other various factors. And then you can view that data breakdown specifically using the selection highlighted there. And so after you take that chemical list, you maybe narrow it down based on high activity, low activity, very sensitive, not so sensitive. You can send it to our PBPK tool, where you can generate chemical concentration predictions. And on our PBPK tool, you can choose between species. You can choose if you want it to be for human or rat. You can choose between 3 PBPK models that are sourced from EPA's HTTK package. So HTTK package being the high throughput toxicokinetic package developed by EPA and John Wambaugh's group. And you can customize the model parameters such as exposure route, exposure length, simulation length to make sure that you're getting the tissue concentrations that you want for the scenario that you want. And the updates that have happened to this tool this year include we've updated the HTTK package to be as closely associated with the new releases as possible. So now we're at version 2.2.2. There is a new fetal PBTK model that comes with that update of HTTK. So you're now able to predict tissue concentrations for both the maternal and the fetal tissue. And our inhalation model, or the solved gas PBTK model, now accepts concentration units of parts per million volume on top of the micromolars allowed previously. And here's what an update of that PBPK model would look like. So after you input all the parameters that you want, you customize it to your specific specifications, you then generate some visualizations that you might find particularly helpful. So one of those is going to be a line graph, and in that line graph you can show the concentration of the chemical over time in different tissue compartments and tissues such as plasma, lung, brain, or if you're looking at the fetal model, fetal tissue, or fetal brain, fetal lung, or maternal. You can also see box plots that show the Cmax distribution, or the maximum tissue concentration, across all return chemicals for each compartment. And again, you can do this, you can visualize this for each of the solved PBTK models, each of the 3 models we allow you, but you can look at the new fetal and maternal concentrations here as well. Okay, last but not least is the IVIVE tool, and that allows you to take these in vitro points of departure and put them into a larger in vivo context, so that in vitro to in vivo extrapolation. And for the in vivo to in vivo extrapolation, the IVIVE tool, we allow you to customize it similar to how you can the PBPK model. And so you can choose from in-house ICE models or models sourced from US EPA's HTTK package, including that new fetal model. You can customize model parameters, again, such as exposure route, exposure length, simulation length. You can choose a type of activity concentration, the in vitro concentration that you want, whether that be AC50 or ACC. And you can upload custom in vivo or exposure data to overlay on charts, or you can upload your own in vitro data if you so choose. And similar to PBPK, because this also uses HTTK, it allows the new fetal model as well as the new concentration units for inhalation. So one output that you get from this model is box plots that show you the equivalent administered dose based on those in vitro inputs. And beyond just being able to see those equivalent administered doses, before you could overlay your own in vivo data, or you can overlay our default built-in in vivo data. And so a new update that we added this year is now you can overlay those new exposure predictions. So I talked about how we added in those CIEM3 population level exposure predictions. And now you can put those side by side with those IVIVE box plots. And in doing so, you kind of have that hazard assessment of those IVIVE points of departure. You have an assessment of chemical exposure based off of those exposure predictions from CIEM3. And by seeing the intersection of those two, the intersection of that hazard and the exposure prediction, get a better idea of potential chemical risk. So real quick, because I'm running out of time, one of the things that we are working on and that is currently in beta mode is we are working on visualizations for endpoint-specific data. And so in previous releases, the visualizations that you can find on the search page are primarily CHTS curated high-throughput screening data and bioactivity. And so we're working very hard to allow users to better visualize other data sets as well, including things such as acute lethality or cardiotoxicity. And so this is quite the task, and there's a lot of variability and a lot of specific things you need to consider with this data set. So it's currently rolling out, so make sure you keep an eye out for your own specific preferred endpoint. But we have a tree map that is organized according to the organizational structure of ICE databases. You can click out and click down to get to those more specific visualizations, and we're working on adding those slowly over time. Okay, and last but not least, one of the future additions that we are also really working on and is a high priority for us is incorporating genetic enzyme variability in PBPK models into ICE. And so when we say we're developing this workflow, it kind of takes 4 main inputs. So you have the exposure from the parent, we have PBPK parameters derived from OPERA, there's enzyme variability data that we get from EFSA that specifically is variability and intrinsic clearance, and you get predicted metabolites from Simulations Plus Predictor. And by taking all those various inputs and turning them into this kind of workflow where you feed it the exposure dose into a parent HTTK model, you then build a variability boundary around that parent, and then you use that as a feed-in for the metabolites. You are able to get tissue concentrations that are not just one solid, straightforward prediction, but gives you an idea of high population, or the high tissue concentration expectation and the low tissue concentration for those individuals. And What that means is that you're able to kind of target more susceptible populations when you're doing these analyses. Okay, so in summary, ICE is an open access computational tool with highly curated data and interoperable tools intended to support the development, application, and evaluation of NAMs. ICE is continuously updated to address evolving stakeholder needs, and this includes, but is not limited to, some of those updates that I discussed before, like using search with chemical names and synonyms, which was recently added based on feedback from this group. You can have population-level exposure predictions from EPA's SEAM3 model that you can either download directly or you can access through the IVIV overlay. You can access gestational models from EPA's HTTK package in both PBPK and IVIVE tools. You can look at the functional use categories or the role that a chemical may play in a product as derived from EPA's chemical and products database, and we have new quick lists for mixture and ToxCast chemicals. And future updates that we're working on will include the incorporation of additional endpoint-specific visualizations and the integration of enzyme variability into PBPK models. And with that, I, of course, would like to thank the whole Nicedum group. I'm sitting in front of ICE, and I'm very thankful to be able to do so, but it is an enormous team effort, and almost all of us work on this very, very regularly. I'd also like to thank our subcontractors at SciOM who put together the website itself. Yeah.
Do we have any quick clarifying questions? Okay, Dr. Price.
Yeah, just one one quick clarifying question. You mentioned this new the new exposure prediction.
Yes.
That you come. What's that based on, or what is the input to how
So
that works?
that is based off of so the SEAM3 models. It's a meta model developed by EPA where it takes 12 high throughput exposure models developed by the ExpoCast group over at EPA. It weights them against biomonitoring data from the NHANES study, and it kind of takes all those predictions, has a meet in the middle approach to get these population level exposure predictions in milligrams per kilograms per day.
Okay, great. Yeah. Thank you.
Okay, thank you. Dr. Mansouri.
So I guess I have till 3:45 since we skipped the break. Okay, thanks a lot. Thanks for this invitation to present a little bit about opera. This will be just a general overview about opera, was already mentioned, and some aspects of it already covered. So I'll try to be brief and not exceed 10 minutes. Opera was developed basically to help fill the data gaps and bridge the lack of knowledge about certain chemicals that were not tested, and also to prioritize testing in certain cases. So all opera models were built based on the 5 OECD principles for QSAR validation to make all predictions reliable, adequate, and within the applicability domain of the data that is provided. And also we provide a lot of information about the technical information using the model and building it, and also the training and validation set and all the appropriate measures and goodness of fit for the predictions, but also mechanistic interpretation when possible to make the predictions as easy to use and understand for regulatory purposes as possible. So the opera approach to build those models and make the models available for users is to really, first of all, start with the curated open access data so that we can provide those data sets later on after the model is built. And curation is a very important step because, like you've already heard, sometimes some models garbage in, garbage out. They keep the data as is, and that bias the final predictions towards certain aspects of the chemistry or the structure activity landscape of that data set. So we really pay attention to that. We try to make sure that all the code is available. So we only use open source code, and that we provide also on GitHub afterwards. We try to keep things as transparent as possible, and we define the applicability domain and the limitations of the models. Just like it was mentioned earlier, that all models are wrong, but a lot of them are useful, but they are useful within their boundaries, within their limitations. So that those limitations, they have to be provided. So Opera, also to make it as user-friendly and useful to all kinds of applications as possible, is we provide it in different flavors. So we have the command line version, and we have a user-friendly graphical interface version, but we also provide other libraries that are wrappers in other different languages, like in Java, C, C++, and Python, to make the tool itself embeddable in other tools, so that anyone using it within a different application, it's within the MIT license, so that anyone can use it in any way they want. So Opera provides predictions for physical properties, environmental fate, ADME properties, and toxicity endpoints, and it takes different inputs for the chemical structures, but we also have this feature added recently that you don't really need a structure to make a prediction. You can also have a text file with the identifiers of the chemicals. You don't have to look for the structures if you have the CAS, DSS, Tox ID, or INSHI key. And the input file, you can also mix all those together. The tool itself, it will figure out which is which and give you predictions based on those. You can download the package that you need from GitHub, and just for information, it was already downloaded over 6,000 times from GitHub. So in the latest version, 2.9, we updated a lot of models. So some of the physical properties models were updated in 2.9, adding a lot of chemicals of interest to regulators. Some of them are PFAS, and I'm coming to that in the next slide. But we also added some new models for ADME properties, like fraction unbound, intrinsic clearance, and KCO2 permeability. And we're going to update some of these models also in version 3. So stay tuned. And about PFAS, since we talked about this already today, these chemicals are very important. And in Opera, we're paying a lot more attention to such chemicals of interest for regulators. So just to point out this publication that came out a couple of years ago, and it was done by an independent group comparing Opera predictions, or comparing predictions from different tools, and it turns out that Opera is one of the best tools for predicting PFAS, specific PFAS. They did not compare, of course, all the properties, but some of them are present in Opera. And just to go back to my point earlier about PFAS, this study was actually done before we even added the last version, improving the predictivity for PFAS and adding PFAS to the data set that I was mentioning here. So this was prior to 2.9. And the point here is that you don't really necessarily need PFAS chemical or a lot of them in your training set to be able to predict PFAS, which means that some of the nearest neighbors that were used to make these predictions are not necessarily PFAS. So even the most nearest neighbor does not have necessarily to be PFAS, because similarity is relative to the endpoint. So the tool itself or the algorithm will figure out which are the most similar for that endpoint to make a prediction. And it does not always pick PFAS as the first neighbor to predict PFAS, meaning that what makes PFAS is those, fluoride and the structure itself. So if those fluorine atoms were substituted by some other halogens, it will not be a PFAS anymore, but it will still be relevant to some endpoints, because sometimes that's not the most important thing for that specific endpoint. It might be for some endpoint, but it's not for all of them. So in Opera, we also have, in addition to those single models, we have these collaborative modeling projects that were included, like SERAP, COMPARE, and CATMOS. So SERAP and COMPARE are for predicting estrogen and androgen receptor activities, and they were led by the EPA to help with the EDSP program. And these two were actually already mentioned in the EDSP white paper, highlighting the necessity and how NAMs can be used to screen for endocrine disruptors. And CATMOS, of course, it was already mentioned, and there is the study that was mentioned yesterday to use it even more for regulatory purposes. So this is important to me because a lot of times QSAR models are used in a way that the only thing or the only output that is used is the prediction itself, leaving out a lot of other very important information like the applicability domain. A lot of predictions were used because the tool will give you a prediction no matter what. It's up to the user to see whether or not it's in the applicability domain. Of course, the model developer, they have to define the applicability domain, and we have that in Opera, but we still give you a prediction even when it's outside, because a prediction is better than no prediction, but you need to pay attention to that information. So in Opera, we provide two levels of applicability domain. One global applicability domain based on the whole training set, and then one local to make sure that your chemical is not within a local minima or a local empty space in the landscape. So that's very important. We also provide accuracy index that is specific to that prediction and specific to that model. And a lot of other information like the experimental value if it's existing, and the 5 nearest neighbors, and their identifiers and their structures as well. Another important aspect that I would love to see in other QSAR tools is the standardization of the chemical structures. So when a modeler builds their own model, they prepare the data in a certain way, or they prepare the chemical structures in a certain way. That specific workflow that was used for the training set, it should be applied also for the test or for the predicted chemical, so that you have consistent predictions. Because like sometimes you take the same chemical that is written in different ways, different SMILES codes, and then it will give you different predictions because it's not the same representation. Having this type of standardizer in the tool itself will make sure that it's standardized back to the same way the training set was prepared, so that you get the same exact prediction every time. So this is very important, and I wish to see it more in other tools. So like Victoria previously mentioned in her nice presentation, Opera predictions are already on ICE. So if you don't want to download the tool and have it on your computer to make predictions, you can go on ICE and check the predictions from there and download them. You can also check them on the API dashboard, and you can download them or look at them chemical by chemical, or also in batch search. Opera is also available on the FDA's Precision platform recently, so you can also access the predictions from there. And most recently, we added a plugin also in the OECD toolbox, the OECD QSAR toolbox, so that you can have Opera run its predictions in comparison to other tools, for example, or do your profiling within the OECD toolbox and include Opera predictions in the same report, so that you don't have to upload them later on or do it separately. it was a feature that was needed in the QSAR toolbox. And with that, I would like to thank the whole team who participated to OPERA, and all the collaborators, especially from the EPA, like Tony Williams and Todd Martin and many others. And of course, all the international collaborators who contributed to the 3 collaborative projects, SIRAP, Compara, and CAMUS. And thank you all, and I'll take any questions or comments.
Do you have any clarifying questions?
Thank you, Mal. Great presentation. The slide you showed where there was the manuscript comparing the different models, one of the models was Nicetum, and then it showed opera.
Yeah, I should have removed that one because that was a different model that was provided prior to opera.
So all predictions in ICE now are from opera?
Are from opera, yeah. Yeah, good eye, thanks.
Okay, there is no, oh, Denis, go ahead.
Sorry, just, yeah, excellent talk, Kamel. Just a clarifying question. When you showed the neighbors on your slide for a particular compound, to be clear, so you always show the neighbors whether or not the model that you use is a k-nearest neighbor model or a neural network or random forest, you always show the neighbors, whatever the type of the QSAR model that you use, right?
Yeah, that is true. That is true, and I use the descriptors, the exact descriptors that were used, the final descriptors selected for that model to identify the nearest neighbors. So it's different from model to model. Yeah.
Dr. Marty?
Great presentation. Just a quick question. So is there flexibility there to input your own parameters? So for instance, if you're doing experimental data generation for, let's say, IVE parameters, you can input those and adjust the models, or no?
No. But we can use your data later on. If you provide us your data, we can use it to include it in the training set and then maybe update the models. Yeah, so if you have data, go ahead, Nicole.
Yeah, just to add on to that, I mean, it's an interesting idea because right now we do have the ability to upload your data, like your own data, if it's in vitro data. So, you know, if you've generated your own in vitro bioactivity data, so you have your own AC50s from in-house assays, you can upload those as inputs into the IVIVE workflow. You can also upload your own in vivo data as a comparator, right? But what you're saying is, can you upload your own like clearance data or fraction unbound or whatnot? And that it's a nice suggestion. I mean, I'm going to take that as a suggestion, put it that way, because I think it would be pretty straightforward to implement.
Yeah, thank you. We noticed that when we're building models, generating those data usually refines the model, so it can be helpful.
Thank you, Dr. Mansari.
Thank you.
Okay, so the next 2 presentations are very quick delves into the topics. They're just 5 minutes each. So I'd like to welcome, the first one is Dr. To.
Hey everyone, my name is Kim To. I am a contractor supporting Nicetum, and today I'll be presenting the DAS app, a web application to predict skin sensitization using defined approaches. So I know y'all know all about skin sensitization, you know all about these defined approaches, but I'm still compelled to give some background information. And so with skin sensitization, you know, this affects up to 20% of the population, and really what we want is to get human relevant predictions, right? And so we can use adverse outcome pathways, knowledge about human biology, and really just leverage these resources to create something that is more human relevant than the in vivo methods. So here's the adverse outcome pathway for skin sensitization, which y'all have seen many times. Just note there's 4 key events, and then you have your adverse outcome. As I said, there's those in vivo test methods, which have been used historically to test for skin sensitization, and these map to key event 4 and the adverse outcome itself. Of course, in recent years, there have been developments of non-animal testing methods that map to these earlier key events within the adverse outcome pathway. However, as individual methods, they aren't recommended as standalone replacements for those animal methods. And so what's recommended instead is that results from these multiple assays mapping to those key events, as well as other information that might be relevant, be combined using defined approaches in order to get that prediction of skin sensitization hazard and potency. And so we have these defined approaches for skin sensitization that have been developed and have been accepted by the OECD for hazard and potency predictions and by the US EPA for hazard predictions. Here are 3 diagrams showing the defined approaches for skin sensitization that are available within the DAS app. That's the 2 out of 3, the key event 3-1 sequential testing strategy, and the integrated testing strategy. And really, you don't need to see too many of the details, but you'll see some of those key event-based assays, and then just a very structured way of interpreting that data to get your toxicity prediction. When compared to human reference data, these defined approaches for skin sensitization do perform equivalently or better than the LLNA for hazard identification and potency prediction. And so essentially what we have these defined approaches for skin sensitization. They're non-animal approaches. They could fully replace an animal test to identify skin sensitizers. But as you saw in those diagrams, in some cases, the logic might be difficult if you have a lot of data that you're trying to analyze. It might be error prone when you're applying it manually or in Excel. And so we have created the DAS app. This is an open source web application that allows users to apply those defined approaches for skin sensitization without really needing any coding knowledge. And you can access it via web browser. There's a link and a QR code there. So when you open the app, the first thing that you'll see is that everything is broken up into 5 steps. The first one is to select the defined approaches that they want to apply, and that's going to be the 2 out of 3, the integrated testing strategy, and the key event 3-1 sequential testing strategy that I showed you diagrams of earlier. In the second step, the user is going to upload their data. We accept 3 file formats. It's tab delimited, comma separated, and Excel. And we provide data templates to help users with data preparation, but you don't have to use the templates. There's also documentation throughout the app and in the user guide to help with that data preparation. So they've selected their defined approaches, they've uploaded their data. The app then says, okay, with these defined approaches, which endpoints do we need data for? And so for each of those endpoints, there will be a section with a drop-down menu containing all of the column names from the user's data, and they just select the column that corresponds to the given endpoint. And so there's really no requirements as far as column names or column ordering, and you can keep metadata in there if you would like, in your user data if you would like. So after the user has finished selecting all of their columns, there will be a quick step to review the values in those columns and flag anything that might violate the formatting requirements. And that just helps you know if the defined approach is even going to give you something that's relevant, or if you need to go back and update your data and fix the formatting. So lastly, you'll get your results. That's step 5. And the defined approach predictions are going to be appended to the user's original data, and they can download it as an Excel file or a tab delimited file. There's some color coding for the columns, and that's explained within the downloads as well as on the app itself. So with that, for my summary, we created the DAS app, and it enables users to apply those defined approaches for skin sensitization. Those are the non-animal methods that we can actually use to replace an animal method. And there's ongoing work for it, I believe. I know that there's been some testing for other assays, and I would like to update the app as soon as those are approved. And with that, here are my acknowledgements. Thank you to the NICEDM group and Judy Strickland, who is retiring. And thank you.
Any clarifying questions from Sagato members? Okay, great. Thank you so much. We will move on to the other 5-minute talk, Dr. Boreal.
Yeah, thank you. I will present you the development of ChemMaps or the new version of ChemMap to explore the chemical environment. Okay, so what is a chemical space? The first definition. So a chemical space, it's basically a space where you put your chemical on it. It's based on molecular descriptor. It can be based on bioactivity. It can be based on fingerprint, on all of these kinds of property. So why So basically, if you, for example, that is an example of the chemical space. Is dot is the chemicals, and is based on a similarity metric, and is based on the projection method like PCA, MDS, and UMAP, for example. So why is it interesting to navigate in the chemical space and to represent the chemical in the chemical space? Is to look at your chemical of interest. Can be PFAS, can be another chemical with activity of interest, and you can analyze which kind of other property, which kind of chemical is around, and you can also project on this 3D space the property like physicochemical property or bioactivity. And by analyzing the chemical space, you can extract some information on some element from your chemical. Also, it can be interesting to read across to find some analogs by looking at the closest chemicals that you are looking, do some drug repurposing, and also to define some domains of activity, for example, in the chemical. So to do that, we need an efficient tool of navigation. So we need to develop like something that user can use to navigate in a 3D space and to see which chemical or which kind of property there is. So it's why we developed like ChemMaps. We developed the first version of ChemMaps in 2018, where we have more like 80 different unique users that connect themselves on ChemMaps. So in this new version, the first version was very limited on the number of chemicals, and we literally extend the number of chemicals, and we develop new map, and new property on this new version. So I will give you just a quick live demo of ChemMaps. If you can see. I can see on the back, you cannot see on the front. Okay. So it's working. So welcome on ChemMaps. So basically it's a website. It's freely available, so you can connect yourself. So when you connect yourself, you can choose on one of the 3 different maps that are available to navigate. The drug map based on the drug bond, the DSS max or the DSS tox, the tox 21, on the PFAS map. So if I'm looking at the PFAS map, for example, so basically it's a space where each planet or each star is a chemical. Everything is interactive. You have a panel of interaction here, where as you navigate, the information is changing. So as you can see, all of the chemicals here are PFAS, and you can decide to put like different properties that you choose to put on the map. For example, the estrogen receptor binding, the androgen receptor binding, the LOPI, the molecular weight, and all of those kind of property on it. So it's based on the opera molecular property. So you can play with that, and you can extract, for example, if you are looking for analog, you can decide to extract the closest neighbor of one chemical. If it's working, I need to reload, but you can visualize the chemical on the map. So everything is interactive, and you can navigate. And if you click, you can navigate also the chemical on the big DSS tox maps that include like 2 million chemicals, the whole DSS tox. So for example, if you visualize the chem maps, the PFAS on this chemical, you can see they are at the extremity of the map, and they are relatively different to the other chemical in terms of molecular property and the low density part of the map. So in the new version, what we did too, we include the tox 21, we include all of the results of the tox 21. So when you choose your map, you can choose the property you want to put, but you can also put like the different property, the different result from the tox 21 on the toxcast, and you can choose by assay, or you can choose by group of assay, by gene, for example. And if I choose like TP54, for example, as a target, you can see which on the tox 21, on the 10,000 chemical on the tox 21, which chemical have activity. You can decide to color, for example, the chemical by the number of active assay by chemical. In the panel, you see the lowest AC50 with the lowest AC50 and the number of assays the chemical is active. So you can navigate with these 4 different maps. You can navigate the different property of the chemical, and you can choose and visualize different things that you want to see, like physicochemical property or bioactivity, for example. So if you can switch to the presentation, please. So I invite you to connect yourself. I don't have really time to develop all of the aspects of ChemMap. We have also different map of the IS activity. But we are still working on development of ChemMap 3, so we are looking to develop a standalone version when you can upload your chemical. We are also developing some training on also a completely customizable map where we are not limited on the way we have project the chemical on the map, but you put your coordinate and you can use a tool of navigation on it. We're also working to link ChemMap a little bit better with ICE. So with that, I invite you to connect yourself on ICE. I would like to thank you and thank my group for this work.
Do you have any? Oh, Dr. Tall.
It's really neat. So how do you place chemicals on that map? What is it based on? And then it's nice, but it's like in a way also really overwhelming. So how can you use it to find kind of like emergent patterns that could inform an understanding of how a chemical might cause biological effects because it's grouping, for example, with many other chemicals with some sort of similar information?
So the map is defined based on the physical-chemical property from the 2D and 3D, 1D, 2D, 3D descriptor. So basically, if you are looking at bioactivity, you can look, there is different way you can do it. You can look at if the chemical is active. We have a table look where you put your chemical and give you if there are activity on the ToxCas and the Tox21. And with that, you can project on the map more focus on your chemical. Also, we have some search bar on ChemMaps when you can put the name of your chemical, and it will put you, it will put you in the area of the space where your chemical is. And you can also upload a group of chemicals. If you don't have any information, you can upload on the map and see where the chemical is on the map.
Do you have any additional clarifying questions? Okay, looks like no. Thank you very much. Okay, so this is the public comment section, but want to acknowledge that there was no written comments and no registrations for oral comments for this section. So we'll move straight into the SecAtom discussion. Again, we're going to start with the lead discussants, which for this topic were Dr. Forge and Dr. Price.
Thank you very much. Excellent talks. Congratulations to all the speakers this afternoon. It's always very interesting to see the progress from one year to another, and as always, there are many progress this year compared to the previous year, so amazing stuff. I'm going to start with just underscoring those presentations and those progress in the context of where the field of cheminformatics actually is. And everywhere you look in 2023, it's all about AI and prediction and predictive methods and computer-based prediction of some sorts, right? And so I think all these efforts done by the NIHS and overall this community is very important. So thanks a lot for all the pushing for the application and the development of those in silico techniques. When it comes to I'm going to go, I would say, by the order of the presentation and by the order of the question, right? So I'm going to start with the presentation on ICE, especially with some feedback of the comments that we did last year. So the database access via the API it's a big win, I think, for everybody. So congrats for the development of that. I think when you have like lots of queries, using the API is so much better. It's game changer. So congrats for that. The exposure prediction, same. I think that's a fantastic tool for the community. So thanks for doing that. The formulation and the mixtures, I think more work is needed on that. And obviously I understand the challenges and understand the lack of actual data. And yesterday we saw that really cool slides about this 20 plus formulations that were studied. I think it was in the talk of Dr. Allen, and more data is needed for those analysis. But having that in ICE is critical. The more information you can put in there, name of the surfactants, trying to get as much information about those formulations is really, really, really important. you guys did an awesome job at implementing one of the remarks from last year, which is like when you get a chemical name, usual name or chemical synonym name, then you just like enter that and then you get the full search being done. That's fantastic. I think it was one of the main comments of last year. So it means that for all the SACADM members in the future, you can see that when you do a remark, then next year, the remark has been addressed. So congratulations. They do pay attention here in this building, which is great. The integration with the CompTox dashboard from the EPA is seamless, so you guys have done a fantastic job for that. I was playing with that last weekend, just like you can really switch from one tool to the other in like just one click. It's fantastic. Everything around the PBPK prediction tools, really, I think it's one of the coolest thing and the most useful addition of this release, and that's really useful for the research community as a whole. Like, for example, the fetal PKPD or PBPK model, really, really cool, really useful for so many different applications. So congrats for that. So ICE, fantastic. The only thing I would need to add for ICE perhaps is that when it comes to the data sets, so you have many data sets that can be linked to 3D structures and chemicals, binding modes and binding sites. When you have like ER or AR data sets, for many of the chemicals that you already have in those data sets, you actually have a potential binding site, a potential binding mode of that compound. And I think having that data or a link to the PDB is quite important there, because it's very much relevant. Having more data on metabolism is very important. I think that goes back to what Kamel was saying for Opera, and so that's a perfect segue with the next step. Kamel, so the name of the tool is Opera, and I think Kamel has been the perfect chef d'orchestre, right, for this tool. Amazing job as always. The GitHub is very much regularly updated, which is like great stuff. For the industry, the command line tool is very much well appreciated as well. We can use that on our own server, and we don't need to upload any sensitive data on any server. Fantastic, love it. Something that Kamel said, like 6,000 plus downloads. That's a great metric. I would actually love to see that metric for ICE. Like what's the number of users? What are the users prefer? Which tool is the most used? And getting the user feedback directly on the website. Opera is definitely a growing series of models. You did reply, Kamel, on showing the neighbors in the prediction output, whatever the actual machine learning algorithm that you are actually using. That's great. It's a great way to show the transparency about the type of the chemical space that you have in your model. But the thing I would add for Opera is always a disclaimer. So a disclaimer about the model's limitation. So for example, you have a particular data set, you build a series of models. Always try to have a little paragraph that strictly or explicitly say that the limitation of the data set that was used for building that model and the limitation of the model itself in terms of, for example, if you have a set of binding affinity, for example, what was the ranges basically of the activity that you use, etc. So if it's going to help, for example, if your model makes a dramatic extrapolation, you need to show a disclaimer and you say, oh, careful, your model is dramatically extrapolating from the training set. Something like a warning, as many people, as you said, like in any case, the model will always output something. Make sure that disclaimers are in place. What else I want to say? The structural curation. Kamel and his team has done a fantastic job on implementing all the best practices for structural curation in the tool. That's really state of the art. the integration of Opera in the OECD toolbox is very much practical, because in many companies you just use the OECD QSAR toolbox, and then Opera is already in there, so you just only run one tool instead of like 3 or 4 for the same data set. It's always faster. It's great. For ChemMaps, great job, Alex, with all the progress. As you know, ChemMaps is close to my heart because it was born in my former lab at NC State, so it's always great to see the progress on that tool. I think having the direct links with the ICE and then the CompTox dashboard will definitely help the tool, because it's gonna answer the question about, hey, you want this chemical, you want to put it on the map, in one click you're going to get that projection done. So that's going to answer that question that our colleague here was asking. Okay, final stuff. Applicability domain, yes. Here I'm going to talk a little bit about the specific cases of agrochemicals. As we all know, in the next decade or so, the chemical space of agrochemicals will probably change a bit because of many agrochemicals being removed from the market. And so there's going to be a shift in terms of scaffolds, modalities, mode of actions. So many of the tools that are accurate/reliable today will have to be retrained, will have to be adapted to all these new modalities and all these new scaffolds. So let's make sure that when we build tools, they are easily retrainable with new data sets coming up from the industry. Another question that is rarely addressed, but when you discuss chemical space and applicability domain, it's good to define it, but it's also good to learn from that chemical space about what else is needed, right? So you have these different data sets in ICE or in Opera, and then you can realize that, hey, in that particular region of the space, you miss a lot of cosmetics, you miss a lot of agrochemicals. So I think always answering that question, what else is needed to complete your chemical space, I think would be very much relevant. Overall, I think it's pretty much all the key details I wanted to make. Overall, amazing job. Thanks a lot for the great presentation this afternoon, and thanks a lot for the invitation as always.
Yeah, I think maybe some of the speakers will appreciate the chance to respond to it. And I know Dr. Kleinschreier is going to start, but just let me know if any of the speakers want to respond to any of that.
I just, first of all, thank you so much, Dr. Forsch. As you noted, we pay close attention to all of the feedback that we pretty much assign you as a reviewer to this section every single year, because you give such outstanding technical suggestions that we implement throughout the course of the following year. So you may be roped into doing that as a member of the public since you are rotating off of SACADM. But anyway, I just wanted to very quickly give some numbers, because when you brought up the sort of the desire to know, what is the sort of equivalent user count for ICE. Obviously, ICE is not a standalone piece of software, so we don't have download numbers, but we do run Google Analytics reports on it on a monthly basis. And so I just went and looked back quickly over in the spring, like over March, April, and May, and we averaged between 700 and 900 users monthly. So like in March, during the Society of Toxicology meeting, we had a pretty major spike. We had like 950 users that month. So it's obviously getting used. And those are sessions. Those don't necessarily represent unique users. I mean, if the same person is using it every single day, that's going to, register as 30 different sessions. But it's, I think, being taken up broadly across the scientific community, and we are getting a lot of feedback from our federal agency partners that it has been very useful for them in their regulatory decision-making processes. So thank you.
Yeah, Dr. Mansouri.
Thanks a lot, Denny, for the great suggestions and the comments. I really appreciate that. So one quick note about the transparency, also about the applicability domain. I mentioned it in the presentation, but I didn't go into details, so I don't spend too much time on it. But we have QMRF reports, which is the QSAR modeling reporting format files that details all the technical information about the training set, the test set, also the statistics about the model, and a lot more details about the applicability domain and how to interpret those indices, because like the global applicability domain is just yes or no, in or out, but we also provide the local applicability domain index, which is a range from 0 to 1, so 1 is the highest. So the QMRF details all those important information about how to interpret the output and what the tool is providing. And those QMRF reports are built by models, so it's going to be specific to each one of the models. The new models, I would say that the 3 new models, we still don't have QMRFs for them, but we're working on it. But all the previous models were already generated QMRFs from them, and they are also available on the GitHub repository of Opera. Thank you.
Okay, we're going to move to Dr. Price, but just a reminder to any other CICATA member or ad hoc member that wants to participate in the discussion, if you can use the raise hand feature at this time so we can get the order set up, please.
Yeah, I just want to start off by echoing the great comments that were just made about the team and all of the work that has gone into the computational work. So unlike Dennis, I haven't seen this a million times before. This is my first time seeing it, but I would say it's a very, very impressive set of capabilities. And so the notes that I took that I'm going to dive into, I'm not going to rehash over kind of all the software, because I think Dennis did that really, really nicely and covered that well. So I'm going to turn my attention a little bit to ways that I think this is used maybe out there in the community, or new technologies or different things that we might want to interface with or think about. And this is going to be a little bit broader because I was taking certain notes throughout yesterday and today and on things that I thought were relevant to computation, read a little bit large. So I'm going to talk about that a bit. So in terms of like tools that would be useful or prioritized, I mean, one area that that I think is quite exciting that a lot of us are thinking about these days is like with large language models and things of that nature. And I think it's very interesting, and we had a little conversation about it last night, in terms of the ways that people might interface or ask questions of these databases. There are obviously huge issues in terms of hallucinations, accuracies, things of that nature. But I do think hybrid models that try to take advantage of the strengths of databases and looking up information and so forth, coupled with the flexibility of asking questions and getting responses in plain English. And I think that's clearly a really interesting place of interface going forward. This notion of more integration around metabolism and how toxicity and metabolism interface, I think, is really interesting. A couple of things that come to mind there are there's really good emerging tools in metabolomics now, where you can get, we're looking at, the ability to get 150,000, metabolic features, and this is becoming actually quite inexpensive to do. You can get, tens of thousands of identified metabolites. So that's all coming online. And I think one of the really interesting questions in medicine as well as toxicology is, in medicine, I refer to this as like the long tail of medicine, the idea that you can, how much of this little bits of information that you're gathering is actually relevant. I think in an earlier comment I mentioned that in genomics, we've now discovered that long tail actually exists. It really matters as you get to hundreds of thousands of little variants that you add up. It increases your explanatory power massively. We didn't actually know that at the beginning. And so metabolites and proteins and these other omics, I think, are going to go through a similar period now. And so as we get into that really long tail of metabolites, I think that in particular is really relevant to toxicology, because so many of those molecules, that are in that long, small tail are going to be, some of them will be health beneficial, and a lot of them are going to be toxins. One of the things that we also know for metabolism is as people age, the error rate of enzymes goes up, and so the fatness of the tail in metabolites gets larger and larger. That is an accumulation of of off-target effects of enzymes. That's like a natural, you can produce your own toxins internally. Thank you for body. So that's like an addition, as well as what you're getting exposed to from the environment. So I think that's like a huge area of opportunity. And some of those things are even going to be moving in the commercial space as well as in academia. So I think we're going to have over the next 5 years or so a pretty huge flood of additional metabolites. We're starting to be able to measure more than we've never measured them all before, so we don't even know how many there are there. Whatever we've maxed out to is kind of what we know about. So that's one big area. A second area that I think is pretty interesting for integration with metabolism are the fact that you can build out these genome scale metabolic models of humans. And so some of these kind of things might be really interesting to interface with from the standpoint of toxicology, especially if you can establish, the toxin, does it have an effect on a particular enzyme, on different systems? Those things are probably possible, adjacent to the kind of models that we heard about, today that are really terrific. But that's another big area. Following up on that, I just want to come back to the notion of digital twins. So we talked about that some in the last session. This is an area I work on as well. Those, I think, are going to be incredibly useful in the space of toxicology. I've spoken to some people here about that before. So just as by way of background, so for example, we've built a digital twin model for brain health. And some of the really interesting things that come out of that, without getting into too much detail, is that you can simulate the small effects over long time scales. One example on the positive side, if you're low in vitamin D, you have, by epidemiology, you are 4 times as likely to get Alzheimer's disease. Hazard ratio is 0.23. And so you have this huge observed effect. We don't include it in recommendations for prevention because when people have run RCTs, they find that it doesn't work, and so you throw and you say, oh, it's correlation, not causation. Now that might be true, but in digital twins, we can actually simulate the known mechanism of that, which is, it's tightening regulation on this reverse cholesterol transport system. That's not really relevant right now. But the reason I bring this up is because when you run the digital twin simulations, you can actually simulate the clinical trial that's necessary to see the effect if it is just as big as it looks like and 100% causal. And the answer is they would have to run that trial for about 10 years. And these trials are typically like 6 months, 3 months. That's up to 3 years is the longest. And so what that means is that we throw away all this actually probably valid prevention because of the length of time, and economically it makes no sense to do that on a compound that's that cheap. No one will ever run that trial. Now, I only bring that up because the reverse is almost certainly true in toxicology, which is for all these compounds, there's probably many of these compounds, right? You take it, one of the big issues that we deal with is, all right, if it doesn't cause acute toxicity, which is a different thing, if we're talking about something that is chronic and it's going to lead to a significant increase in cancer in 20 years or Alzheimer's or whatever we're worried about, we want to know that in a way that doesn't require us to just look back and see, oh, oops, we shouldn't have done that, for the last 30 years. And so I think that's one of the big advantages of these kind of digital twin models is the ability to simulate how much does it matter if we have this measured impairment to this regulatory system or this enzyme or something. And because in the digital twin models, at least the kind that we've done and that others I'm sure will be building, you can simulate the course of lifetime. That means that you can ask questions that let you go across these multiple timescales. So that's another area that I think is incredibly useful for toxicology, at least for chronic things. Acute is a little bit different, right? We find that out faster and know right away, but that's an area that I think we should really be thinking of a lot. A couple other things. Microbiome, I was happy to see that was mentioned a few times. I do wonder, I think it was yesterday it was mentioned that, like the predictions for toxicity from like oral is not as good as skin, for example. And I do wonder if one of the reasons for that might be chemical transformations, because, the microbiome, we know for drugs it metabolizes about 13% of drugs. So if you're on a clinical trial, 13% of the time you're not taking the drug that you think you're on, and so forth on average. And so there's, a pretty big effect there. We've actually shown the effectiveness of statins is much more predictable from your microbiome than it is from your genome, for example. So you can get into all kinds of things like that. Obviously has to have big impacts on toxicology. L-carnitine, for example, which is in red meat and other things, gets converted in the microbiome to trimethylamine if you have certain microbes. If you don't, then it doesn't. Phosphatidylcholine, compound that's good for your brain, microbiome turns it into TMA, it becomes TMAO, so forth. So there's all kinds of things that either become toxic or become not toxic. So that strikes me as a really big area of opportunity as well. Other area, topic, which we got into a little bit earlier this morning, was capturing variability. And I do want to add a couple of thoughts there. I thought there were some really good comments on that earlier. Computational methods often do, especially if it's machine learning, do better with variability. And so I think someone else brought this up, but I just wanted to emphasize in the context of computation that there is a little bit of a tension sometimes between reproducibility and variability. One concept that I remember getting into a debate with an experimentalist around this, which is if you're trying to build like a transcriptional regulatory network model or something like this, are you better off running, different transcription factors every time? Or should you do replicates of 3 or 5 or 8 so that you know specifically? And I argued, unsuccessfully in this case, that replicates were a complete waste of time and you should not do them. Now that doesn't mean I mean that across in general, but I mean if your point is to learn and network, you just get more information by having the new thing. Now if you're trying to identify an association, sure, you run replicates. So that's just an example, but I think that comes up in the context of what's being talked about here, which is there's probably similar trade-offs that come up where if your goal is to understand a system, you're better to try to scatter it as diversely as possible because you're trying to get something that will give you diversity. And if some of those, and if a particular measure is bad, right, you haven't replicated it to the nth degree, but you're not actually trying in these cases to understand that interaction. You want to understand the system. So I'm not sure to what extent that would, come up to be relevant in what you're doing, but just something to consider, which is that if, depending on those differences of your objective, you do have this different trade-off between, how solid is the single interaction versus how spread out are you in terms of understanding what risk is. And I imagine that comes up, especially as we start thinking about heterogeneity in populations, which again is a huge advantage of the digital twins because you can simulate the effectiveness on a per-person basis. Oh, there's one other thing I wanted to mention on the digital twins is because you can simulate the trajectory of a person, you can of course do the same on populations. And because you can do this, we've done this a lot for brain health, so you do 10 million digital twins, for example. You can then compare that population and different mechanisms with different error rates against the population averages of what comes out. So what that would let you do in toxicology then is you can observe known effects of the toxins on certain systems, and then how much variability there is in that. And then in the digital twin, you can find out if that explains the rate at which you see the emergence of different problems in the population. So there's this really interesting thing that happens when you've got the digital twin type approaches in that it unlocks different kinds of data for validation, because you can look at population spread and distribution in pockets and subparts of the population and differentials between them and on and on and on in a way that you can't do if you have just like a static model or a machine learning, linear model of some process to some endpoint. So they're really powerful that way. Let's see here. And then in terms of promoting, one other thing that I thought was interesting, this is from the first day, it looked like in some of the computational approaches that they often really agreed with each other. And the question, of course, is whether or not, and as you compare those to like the animal models or the outcomes, one thing that I think is really interesting to look at is in the correlation of the error rate between different kind of computational approaches. To the degree to which you can have approaches whose error rates are uncorrelated, then obviously the error rates become, you can sum those up so the error rates become multiplicative if they're actually independent of each other, which lets you drive to super accuracy. The degree to which the error rates are correlated means that you can't do that. And so it's just one of the things, you're probably thinking about that, but it's, one of the areas that I think is really interesting is to try to identify classes of models where the error rates are as uncorrelated as possible. That can come from building them off different data types, different kinds of assumptions. So it was just something that struck me in one of the slides I saw early was how often when there was disagreement, the models were really clustered to each other. And the question that comes out of that are they close to each other because they're using similar approaches, or is the fact that they stack on top of each other like a stronger level of evidence? And that really depends on the degree to which those error rates are correlated or not. So just want to put that out there. And then the final thing that I'll say is promoting outreach to community, availability of the tools. First, I think it looks like it's been an amazing job of getting outreach into the community, tools that are used, great user interface, make them as simple as possible. And then, things that I'm sure you're already thinking about in terms of, educational sessions, the open access elements of it, I just think that looks like that's on a really good trajectory. And that's it from me.
Thank you. Dr. Barron?
So after those comments, I have just some very basic suggestions. So from, always going after Nathan. But so for the user experience, I guess on the back end, Google Analytics can be very helpful. But these days also just, for example, when you're running on a background, how long did it take somebody go from one point to the next, right? Their motion with a mouse and etc. For example, looking at, what Alex showed, right? If somebody goes on that and automatically closes that window because it's too complex, right? Allows you to see that without necessarily having focus groups or asking it. And I think the softwares these days are pretty inexpensive relatively to do that. So that would allow you kind of collect that information and then refine the user experience from that perspective.
And speakers, just let me know if you do want to respond, but we're going to continue with Dr. Berger.
I can just say really quickly, we have things like bounce rates, so we don't collect just, user, like number of unique users or sessions. We also have like individual page views and then the bounce rate from that page and the number of click-throughs. So we do get at some level of detail like that, but it's a good suggestion.
Terrific work. Really kudos for the efforts to develop user-friendly exploratory tools for ICE. ICE has a lot of data that's of interest to biologists, and they are not as savvy. They don't go to GitHub, for example. And I think those tools are going to be really important for leveraging the data that you've collected in ICE. So I had a question too about the tracking of tools and metrics. So I would like to encourage your stakeholders to keep investing in these software. a lot of times there's the expectation is you build it and then you let it go. And we can't, these are tools that are going to grow in importance over the years. Please continue the investment. And particularly, I'd like to see some more focus, more resources in improving human-centered user interface design, good data viz practices, how color is used, encoding data, accessibility. I think those features are more needed by biologists and would make these tools more approachable and accessible to a broader group of stakeholders. So just encourage the agencies to understand the importance of that data communication and data value of data literacy, really, and to help that. So just comments on the opera. I'm just so happy that all the data and tools are open access. I mean, this is very important for equitable access and managing, any kind of disparities in access to, resources and research. The Chem Maps was like fabulous. And even the DAS app, automating these simple things are tremendously important. So congratulations for that as well. So thanks, guys.
Yeah, I want to take the opportunity to just second that Ellen said. Those of us that are not experts with computational tools, I really like the training and also the user-friendly ability to put those tools forward. As well as the continued progress. And then just stepping back, I'm always amazed with this section, always so much has happened in just a year, right? And, the fact that, there's always a piece on the computational resources, right? Because there's so much that's changed. And also commending the speakers too, because I know that this was we had a lot to present in a short amount of time, and that was very good. Okay, so it doesn't look like we have any additional hands up at this time for this session. So I'm going to ask if any Sakata members or ad hoc members would like to provide concluding remarks for the whole meeting. There's anything that you want to summarize or say?
Just want to quickly say thanks. It's been a really interesting couple of years. I've learned a lot and really appreciated my time with you all.
Dr. Yushio.
Hi, so just thanks for all of the progress and for the people who are leaving or moving on. Thanks for everything and all of your contribution. I just wanted to, I've been reflecting a lot on the conversation yesterday around this sort of new phase that we're entering, which is the scientific work is done in some cases, and now it's like, how do we start to implement these, and how do we sort of get uptake into the broader scientific and private community? And so I just would encourage you, as you think about communication, to kind of really identify, like, what is it about these like new approaches and new methods that are valuable beyond sort of the animal side of the discussion? So I think there's the scientific and data, there's the reduction in animal usage and the quantification of that. But I think what's going to be really important is that both the developers and the customers, if you will, really need to understand that the data is additive or better than what they're already doing. So I think it's really important to really hone in on, is this more data? Is it better data? Is it new information? Does it actually explain things in a more relevant light, whether it's species relevant or what have you? And I would almost argue to lead with that. So it's like, okay, I'm gaining this scientific information is a creation of new knowledge that's going to help me do a better job. And in addition to that, we're actually, contributing huge to the 3 R's initiative. So I feel like, and I'm happy to talk offline about that as you sort of explore these, but I sort of feel that will help people get grounded in like the amazing science that you've done, and that the whole package is really valuable. So thank you.
Sure. Two quick comments, as you hear. I like to talk, as you can see. I think one of the first things is like always staying open and reactive to the community's feedback, right? So for example, CAM apps, if you hear, so if many users find that there are too many things on the screen, it's overwhelming, just no problem, just put a distance cutoff, that's gonna reduce your number of points immediately, right? Always try to get the feedback from the community and then just like react from that. Things like this. And then the promotion, again, like making sure that when you guys have new tools available, making sure that it's available immediately, like there's a nice post on LinkedIn, on Twitter, on X, right? Things like this, that the community is immediately aware of it, not randomly finding out that, oh, there's a new release of this or something like that, right? But that, at the end of the day, to me, there are two things. There's like the fact that reports are great, but at the end of the day, the things that are the most useful for the community and for industry partners are like tools and very much practical data that can be used by everyone to advance the science. And so I'm so happy to see that you guys are developing tools that can be actually valuable for so many people out there. So that's really great. And then the final thing is that there's so many new chemistry out there, so many new types of chemicals that we always want to stay curious about what's being done. I think that all the different NAMs that we can develop today, always thinking about the limitations of them and how we can overcome, and making sure that those limitations are known by people, that these are not magic wands and magic assays. There's no such thing. And so when you have your particular assay that works fabulously well for kinase inhibitors, they might not work that well for drug-loaded nanomaterial, right? And so always like making sure that people are aware of that, because it's typically not the case. So, but I'm sure that you guys will do a fantastic job at doing so. So thank you very much for the amazing 2 days. That was great.
Thank you. And at this time, I'd like to ask Dr. Sills to provide his closing remarks, please.
So thank you for chairing the committee. Catherine, you've done an excellent job. So this has been an outstanding meeting, recapping the last 5 years of progress and future directions. So thank you, Nicole, Anna, John, and the CCADM committee members and the Innovative team. I mean, this has been really, the discussions we had today are very reflective of the success of CCADM. So in my view, CCADM is the brain trust for innovation around NAMs and other scientific advances for prediction and protecting human health. The only suggestion I have for future directions is to continue to link your successes, your scientific advances, to human biology and diseases. So on behalf of Dr. Wojcik and our NIHS leadership, we thank each committee member for your time, wisdom, and advice for bringing the best scientific rigor to CCADM. Also, we appreciate the engagement of all the speakers and internal and virtual participants of the meeting. So finally, we must thank Melanie and Mary and the entire team for organizing a very successful meeting. Safe travels, everybody, and have a wonderful weekend. Thank you.
Thank you. Thank you, Dr. Sills. Dr. Gordon?
Yes, thank you. I too would like to thank the SACADA members for their advice today. I hope you all understand how valuable the input is. We have a lot of good people at ICFAM and ICEDM, but the different perspective of the information that you bring to us, I hope you understand that, I understand the amount of time and effort this takes. The amount of materials we give you guys is tremendous to read over, and you guys come and give us advice, and we thank you very much for that effort. Catherine did a great job past couple of days chairing the group. Melanie, thank you very much. I can't imagine putting on a meeting and finding out 2 or 3 days before the meeting the cafeteria is going to close. Thank you all for handling our lunches in particular, because that would have been kind of disastrous having everybody leave campus and everybody coming back. That would be no bueno, no bueno. All the speakers, thank you very much for coming. I've learned so much these past 2 days. Anna, you get the prize for coming the furthest. Second time coming across the Atlantic to speak on the U.S. in the past couple of weeks, so we thank you very much in particular. But thank you to all the speakers. I mean, you all did a fantastic job, learned a bunch today. Nicole, for your leadership in ICFAM and ICEDM. Warren, of course, for always pushing the envelope and pushing the science forward. We really appreciate that. Dave Allen and Innovate staff, and the NICEDM contractors. ICFAM would be horrifying without you guys. It would be very difficult to get anything done. Anna Lowett, the other co-chair of ICFAM, I thank her for her work. And let's all have a round of applause for the AV staff. Thank you very much. Really appreciate it. They put on 4 screens up here on our computers, and everybody at home doing a great job. The NIHS for hosting in the first place, really appreciate that. My fellow ICFAM members for all the support you've given and all the work group, all the time and effort, in particular the validation work group the last 2.5 years that we spent writing this document that we got some really good feedback on this week. And the ICADA members as well as that have been involved with this. We really appreciate all the help and effort. And I think that's all I got, yeah.
Dr. Clinchrow?
Well, sorry, you're going to have to hear me repeat a lot of what John said, but I think it's worth repeating. First, thank you all for your valuable time and your incredible feedback. I learned so much about sort of the future of my own group and our program every single year by listening to the expertise that you provide us. So it's just such a privilege to have your time and your attention for 2 full days, and to have it in person sort of guarantees that you are actually paying attention. So that is also amazing. So thank you all for traveling here and being here with us. And thank you to Dr. Page for being an outstanding chair and being very strict about keeping us all on time, and when we are and are not allowed to thank people, and when we're just supposed to introduce ourselves and things like that. She's very, very good at being the chair, even though she didn't get a gavel. I promised her she would have a gavel, and I don't know what happened to it, but I'm sorry about that. Also, thank you to all of our speakers, particularly our OECD partners and our ICADM partners who, either traveled long distances or stayed up late at night to join us online. All of our ICFAM representatives who are here or who are online. I'm really sad that Anna Lowett left early because I don't know if you all know this, but Anna has been the ICFAM co-chair for 10 years. So this is her 10th SACADM, and this is her last SACADM as the ICFAM co-chair. And so I really wanted to make a special shout out to just the tremendous contributions that she has provided in that leadership role. And so we'll do something special for her next month at our face-to-face ICFAM meeting. But Thank you, Anna, in spirit, to your empty chair. I think she's listening. I hope she's listening. All of our public commenters and attendees, absolutely the AV team, who is just so like consummate professionals, so outstanding, makes the meeting run seamlessly and smoothly, even when I like last minute run up into the AV booth and say, hey, I have a new slide for you to just display right now before lunch. Can you do that? And no issues whatsoever. They're just amazing. Melanie, as our DFO, has just been absolutely incredible. Mary Wolf, our SPL director, is just amazing support, and Robin Guy, who communicated with many of you and helped arrange a lot of the logistics here, and Ella, all the folks that have really helped behind the scenes. This would not happen without them. And then, last but absolutely not least, our Innovative support staff and our SciOM subcontractors. They are sort of the life and breath of NICEDM. So you heard from many of our outstanding scientists from our support contractors today, but there's such a broader team behind all the work that you all review for us every year. And I in particular want to thank Stephen Moorfield and Kathy Sprinkle, who are here, who have been leading our program management and our communications and just doing an outstanding job at that as well. And if there's anyone I forgot, I'm really sorry, and it's not personal. Okay, thanks.
Dr. Brownlow.
Thank you. I'm going to start by thanking Dr. Baines for always helping me with the microphone. That's the downside of being short. Thanks, everybody, for being here. It's lovely meeting you in person. Sorry I didn't get to meet some of our participants that are remote. I will not attempt to replicate the previous two or a few acknowledgements because I would probably leave somebody out and I wouldn't like to, but this has been a group effort. It does take a village, so I appreciate everybody who's here, everybody who's behind the scenes that we don't get to see. So please, I hope you feel acknowledged. Thank you all SecAdam members and ad hoc members for your very insightful recommendations, for thoughtful conversations. I know we did give you a lot of background documents, so I appreciate you guys preparing and taking all that into account prior to discussions. So thanks, everybody. And before we adjourn, I would just like to remind everybody that the minutes will be available on the meeting webpage after they have been reviewed by all members and approved by our chair. And likewise, we will make the slides available too as soon as they meet government requirements. Thanks, everybody.
Thank you. Thank you, everybody who supported, participated, viewed. It's been a pleasure to be your chair, and hopefully we didn't make people too mad by keeping on time, but ahead of time. So I would just like to remind everybody that our next meeting for SecAdam is scheduled for September 17th to 18th, 2024 in Bethesda. Thank you very much, and that adjourns the meeting. Thank you.